In this video, we will learn about fertilizer application and pest management. We will learn about fertilizer analysis, how to calculate the cost of a fertilizer plan, speed of application, and application rate. The concepts taught in this video will be important to use when making fertilizer and pesticide recommendations, purchases, or applications. Fertilizer analysis gives the percent of nitrogen, phosphorus, and potassium in a given fertilizer, expressed as percent N, percent P2O5, and percent K2O. The rest of the material in the fertilizer is filler. Phosphorus and potassium are expressed in their oxide forms, but that is not how they are taken up. The oxide forms are just a way to compare different fertilizers, like comparing apples to apples. In this example, we have a 30-pound bag of 20-10-5 fertilizer. This means 20% of our fertilizer is nitrogen, 10% of our fertilizer is P2O5, and 5% is K2O. Let's figure out how many pounds of N, P2O5, and K2O are in the fertilizer. Let's start with figuring out how many pounds of nitrogen we have. We know out of 30 pounds of fertilizer, only 20% is nitrogen. So we take 30 pounds times 20%, or 0.2, to get 6 pounds of nitrogen. To find P2O5, we do the same thing. 30 pounds times 10%, or 0.1, is equal to 3 pounds of P2O5. Finally, we need to find K2O. 30 pounds times 5%, or 0.05, is equal to 1.5 pounds of K2O. If we add these numbers up, out of our 30 pounds of fertilizer we purchased, only 10.5 pounds are nutrients that we want. The other 19.5 pounds is filler. Let's try an example problem. Your soil sample results indicate your field needs 100 pounds of nitrogen and 55 pounds of phosphorus per acre. You want to use DAP and urea to supply the needed nutrients. How many pounds of DAP and urea need to be mixed together to get the desired analysis to apply? DAP, or diammonium phosphate, and urea are common fertilizers. DAP's analysis is 18-40-60, or 18% nitrogen, 46% phosphorus, and 0% potassium, while urea's analysis is 46-00, or 46% nitrogen and 0% phosphorus or potassium. As you can see, DAP supplies both nitrogen and phosphorus, and urea supplies only nitrogen. This means all of our phosphorus supply must come from DAP. Therefore, we need to start by determining how much DAP is required to supply all of the phosphorus needed. In the earlier example, we multiply our total pounds added by their percent element to get our pounds of element added. In this example, we are given the percent element and the pounds of element needed. For P2O5, our percent element is 46%, and our pounds of element needed is 55. To find our total amount of DAP we will add, we will need to work through the equation backwards or divide. 55 pounds of phosphorus divided by 46%, or 0.46, equals 119.6 pounds of DAP we need to apply. Now we know we must apply 119.6 pounds of DAP per acre. If you remember, DAP supplies both nitrogen and phosphorus, so we must still give credit for the nitrogen in DAP. Let's figure out how many pounds of nitrogen are in the 119.6 pounds of DAP that we are applying. We use our same equation from before, and as you can see, 18% of DAP is nitrogen. Plug those numbers into our equation, and we will multiply 119.6 pounds of DAP by 18%, or 0.18, to get 21.5 pounds of nitrogen supplied by DAP. If we need 100 total pounds of nitrogen and got 21.5 pounds from DAP, that means we still need 78.5 pounds of nitrogen we will get from urea. We will approach this problem using the same equation as before. Let's plug in our numbers. Urea is 46% nitrogen, and we need 78.5 pounds of nitrogen total. So 78.5 pounds divided by 0.46, or 46%, gives us a total of 170.7 pounds of urea that we will be applying. So in total, we will be applying 119.6 pounds of DAP and 170.7 pounds of urea. How much would the fertilizer cost per acre if urea cost $337 per ton and DAP cost $315 per ton? In the last problem, we found that we need to apply 119.6 pounds of DAP and 170.7 pounds of urea per acre. Prices for these fertilizers are given in dollars per ton, and 1 ton equals 2,000 pounds. To find out how much each pound of fertilizer would cost, you can set up a ratio. A dollar amount equals 1 ton, and 1 ton is equal to 2,000 pounds. Remember in algebra, if something on the top equals something on the bottom, those two will cancel out. So in our case, we can cancel out the tons on the top and bottom, and that gives us a dollar amount divided by 2,000 pounds. So let's try using this with urea. Urea costs $337 per ton, and 1 ton equals 2,000 pounds. So we cancel out our tons, and $337 divided by 2,000 pounds is equal to 17 cents per pound of urea. Remember that we need to apply 170.7 pounds urea, so 17 cents per pound times 170.7 pounds of urea gives us a total of $29.02 per acre that we will spend on urea. Now let's look at DAP at $315 per ton. $315 equals 1 ton, and 1 ton equals 2,000 pounds. We cancel out our tons, and we're left with $315 divided by 2,000 pounds, which is equal to 16 cents per pound for DAP. Next, we multiply 16 cents per pound of DAP times the 119.6 pounds of DAP that we are applying, and we get a total of $19.14 per acre for DAP fertilizer. If we add these two numbers together, the total fertilizer cost per acre is $29.02 plus $19.14, which equals $48.16 per acre. When using a sprayer, it is important to calibrate your sprayer to ensure efficient application of chemicals. The numbers to use for sprayer calibration should be easy to find. The number of gallons per acre to apply can be found on a chemical label. The speed is how fast your sprayer can drive, or how fast you are willing to drive your sprayer in your field. The inches between nozzles is dependent on your sprayer. The gallons per minute will tell you what nozzle is necessary for that application. In this example, we are asked to calculate the gallons per minute, or GPM, using 25 gallons per acre, 8 miles per hour, and 15 inches between each nozzle. Luckily, there's an equation to calculate this. Gallons per acre times miles per hour times width between nozzles in inches divided by 5,940. 5,940 is the conversion factor that takes into account the conversion rates of acres, gallons, inches, and miles per hour, so we will not need to do all those calculations ourselves. To compute this problem, just plug in all the numbers and multiply it out. 25 gallons per acre times 8 miles per hour times 15 inches equals 3,000, and 3,000 divided by 5,940 equals 0.5 gallons per minute. The nice thing about this equation is that it can be manipulated to find any number. For example, if you know how much you need to apply per acre, your nozzle width, and how many gallons per minute you will apply, you can calculate how fast you must drive your sprayer. How many acres can you spray in an hour if the sprayer has 21 nozzles? In the previous example, we are spraying at a rate of 8 miles per hour. To figure out how many acres we could spray in an hour at a continuous rate of 8 miles per hour, let's pretend that our field is 8 miles long and the width of our sprayer boom. This would give us a rectangular field with a length of 8 miles. Remember, 1 mile equals 5,280 feet, so we multiply 8 by 5,280 to get 42,240 feet for the length of our field. How do we figure out how long our sprayer boom is? Our sprayer has 21 nozzles with 15 inches in between each nozzle. So we should just multiply 21 by 15 inches, right? Let's think about this. Let's say our boom has 5 nozzles with 10 inches in between each nozzle. We wouldn't multiply our 5 booms by 10 inches because that would leave one end without a nozzle. We know that booms have nozzles on either end, so we multiply 5 minus 1, or 4 nozzles, times 10 inches to get a total of 40 inches. Going back to our original problem, our sprayer has 21 nozzles with 15 inches in between each nozzle, so 21 minus 1 times 15, or 20 times 15, equals 300 inches. So we know how wide our boom is in inches. Let's convert that to feet. 300 inches divided by 12 inches per foot equals 25 feet. So our field dimensions are 25 feet by 42,240 feet. So if we multiply those together, our total area is 1,056,000 square feet. One thing to remember in agriculture is that 1 acre equals 43,560 square feet. So to get our total area into acres, we need to divide 1,056,000 square feet by 43,560 square feet to get a total of 24.2 acres. If your sprayer has a 2,000-gallon tank, how many acres can you spray before you need to stop and refill? If you remember, we are spraying at a rate of 25 gallons per acre. If we have a 2,000-gallon tank and divide that into 25 gallons, 2,000 divided by 25 equals 80 acres that we can spray on one tank. Let's switch gears and talk about pesticides. You choose to apply Corvus to your field, and it has a recommended rate of 1.5 quarts per acre. How many gallons of product do you need to buy in order to treat 360 acres that you intend to plant a corn? To sum up this problem, we need 1.5 quarts per acre, and we're treating 360 acres. So 1.5 quarts per acre times 360 acres equals 540 quarts to treat the entire area. But our question asks for gallons, so we need to convert quarts into gallons. 1 quart is a quarter, or 25% of a gallon. Therefore, there are 4 quarts in 1 gallon. We can divide our 540 quarts by 4 quarts per gallon to get 135 gallons of Corvus to spray our field. If the product is $46.95 per gallon, how much will the product cost you? Remember that we are buying 135 gallons of Corvus, and we know that these cost $46.95 each. 135 gallons times $46.95 per gallon equals $6,338.25. If the application fee is $5 per acre, what is the total cost for the product and application? We are applying this herbicide onto 360 acres. 360 acres times $5 per acre equals $1,800 for the application costs. $1,800 for the application plus $6,338.25 for the herbicide gives us a total bill of $8,138.25.